Welcome back, everyone. This is now the simultaneous fit tutorial, which leads us through how we can combine measurements in zfit. And there are basically two ways to do that. One is, the first one we'll look at is to add a constraint. So it can be that we, from subsidiary measurements, know a measured value already and know the uncertainty of it, and we want to incorporate this knowledge into the likelihood. This is the first step we're going to do, and therefore we will build a fit. We can say it in a rare mode, just a B decay with like 120 signal events and 700 background events. Note here we can also, speaking of scikit-hep stuff, we can also use a particle package at the hep units to get all this stuff nicely done. Here we're just generating some data, and that's where the zfit part starts. We define again our observable, which is the BMOS here. We call it like that. We load our data, now created from NumPy, but wherever we want from. And then we create our model in here, which in this case consists of a Gaussian and the combinatorial background. We're not going to do something more complicated. We've seen it already before. We create again our yield parameter. We create two extended PDFs from the signal and from the combinatorial background, and we create the sum. So same thing as before. Again, this is the modularity of zfit. Doesn't really change. Now here comes the relevant thing in. To add a constraint, we can instantiate the constraint here. There is, as a default, there's the Gaussian constraint available, where we get our parameter that we want to constrain, we get the observation and the uncertainty of our observation in, and we can then add this to the loss. We can also add arbitrary constraints, which can be any kind of term. So we can not just incorporate actually other measurements, but if we want, we can also exclude physical regions like that, and putting in a function that if two parameters are, the sum of them is higher than that, then add a penalty or something. So this is just, these constraints actually allow us to fully modify the likelihood the way we want. Of course, pay attention to that, because modifying the likelihood means you're modifying what we're measuring. So there should always be a little bit of caution, but you have the full possibility to implement any kind of function that you want. So we're gonna minimize the whole thing, and we can also print the results. Side note, as you've seen with speed, as we talked yesterday about it with TensorFlow, in this whole speed, in this whole process that we've done, is also the building of the graph and the minimization in there, and we see it's usually pretty fast. So we're close to factor of 2-3 slower usually as to the roof, but it's reasonable fast enough. And here we get our results. Another way instead of constraints is to have a simultaneous fit. This means that we don't have the knowledge from another measurement, but actually we're fitting in two different channels, two different data sets with two different models simultaneously, but we're sharing some of the parameters. Most notably, the parameter of interest, now the one that we know is going to be the same or slightly modified in these two measurements, we share this between the PDFs. Therefore, to simulate that, we're going to look at, I'm not sure how familiar you are with this terminology. If I'm saying now we're doing a rare fit and a resonant fit, what I mean by that is sometimes we have decay channels. So we have a decay that doesn't happen a lot, and we want to look at that. And on the other hand, we have the decay channel, which is basically the same, but it has an intermediate state, a resonance, which happens way more often. I'm talking here about shape psi, for example, for E2K LL decay or something. And then we know that some parameters can be shared there. So we just have one decay which has a lot of statistics, and we have one decay which has very low statistics, but we know that they have basically the same shape. So we're gonna share a parameter in there. That's why the things are called rare and resa. So here we do the same game as above again. We create parameters, we create our space and load it and all this stuff. And now comes the more relevant part, parameters and sharing them. So far we didn't look really into parameters except of just creating a simple one. But there are actually more nuances on parameters. On one hand, we have the independent parameters. These are the parameters that we've known before. And the independent parameter has all the things we've seen before. It has the value, it has limits, we can set the value. That's actually the defining characteristic. We can set the value of an independent parameter. We can't for others. And it has a step size, of course, because it's minimized and all this stuff. Also, in the whole minimization process, independent parameters are the only parameters that can change their value, meaning also these are the only parameters that can get minimized. We can though also create dependent parameters, which are basically just functions that return a value and that depend possibly on other parameters. These can't be changed directly, so we can't say this is floating or not. It's dependent. We can't set the value because it's just a function, so there's no way to set the value on a function, but we can of course set the value on the independent parameters, and then we're getting a value from the value of the dependent parameter change as well. Now sharing a parameter in zfit is, I would say, straightforward, as in when we use the same parameter object in different PDFs, it means that the same parameter object will be used in different PDFs. What we're going to do first here is we create a compose parameter. So instead of using the same sigma, we introduce a scaling, which can be more meaningful for some things to know. And how we do that is we can just create a function that takes sigma and sigma scaling, or let's say just two values, and this is what we return. Then we create a compose parameter, which also has a unique name. And we say that the function, the value that should be returned by this compose parameter is this function above here, and the parameters that this depends on, or that should be given in here, is sigma and sigma scaling, which again allows for whole generality of things. We can compose arbitrary parameters with that. There are also some, as a side note, some pre-composed parameters. There's, for example, a specialized constant parameter. There is a complex parameter that we can directly use. But with this functionality of a default compose parameter, we can just implement anything we want. And here we see now that we can use the same mu as we're going to use for the rare mode. So the mu is fully shared. And here we insert the sigma scaled. So the sigma itself is also kind of shared. Not directly, but somewhat. And then we create also the background, which is a new parameter. And we say the background can be freely floating, that's not shared. Same goes for the yields. And we do the same game again as above. Create our extended models, create the sum. Now, this is a crucial difference to other frameworks like rowfit, how we create a simultaneous fit. A simultaneous fit, surely we can define it as well in the product of a PDF in principle, but if you look just at the loss itself, it's just a sum of different likelihoods, of different negative likelihoods. It's a product of different likelihoods. And since we're already having this loss objects, these NLL objects, what we can do in zfit is we can just add them. And then we get a simultaneous loss, basically just following the mathematical definition. So there is we don't need to have any categories, anything. It's clear now that this model will be fitted to this data and this model will be fitted to this data. We can alternatively also just use one constructor and give in a list of models and a list of data, and they're all matched one by one. And to minimize that, again, I mean, we're doing, this is again the next step, minimize. So the minimization cannot depend really on what kind of loss we're using, which means from now on, things are exactly the same again. So we just minimize it and we create the Hessian approximation. Then we can plot the parameter, print the parameters, and we get the results from our fit. Of course, we also want to plot the simultaneous loss. But given that this is just, these are just object, this is just stored as a list in there. This is actually quite simple. What we have up here is just a more fancy plotting thing. So this is not something you should understand, but what you should understand are basically these two lines below here, which just iterates through all of the models and the data objects and plots them. So it just plots, it's literally just plotting each of the models and the data separately. So let's say plotting a simultaneous fit in zfit is as plotting a simple one. You just do it 2 times in 2 different figures. And this is then what it looks like if you use some more fancy plotting. On the left side is the resonant, then the non-resonant, let's say, channel with not so many events, and this is the resonant channel, let's say, with quite a lot of events. What we can do below here is, again, Hepstead stuff, where I won't go into detail. The only thing that I can show you here, just clicking through, this is the discovery test. If you want to know now, is this a discovery or not? Then we can just click through it. We say which is our parameter of interest, use the calculators, and so we find everything above. We just need to call a very few functions here, and already we get what's the p-value for the null hypothesis, and what's the significance in units of sigma. And we know we've got a 6.6 sigma discovery.